Tonight, I'd like to tell you about a project which is in the final stages of its installation in a hotel in Washington State. It's called the Versix project. And the Versix project is something that we've developed, incubated out of 2-Bit Circus. 2-Bit Circus is a company that I co-founded here in downtown LA. We're not far from here. Many of you actually work there already, so it's nice to see you. And we're hiring. So come talk to me afterward if this sounds interesting to you. Versix is a 4-room, it's almost like a live video game that you play while pipelining through 4 rooms. Let me show you a picture of that. In these 4 rooms, teams of from 2 to 6 people will enter the first room, engage in a sort of live video game experience, interacting with the entire room, interacting with videos, and interacting with each other. And then when the 4 to 5 minutes are up in that room, the door will automatically open, the lights will come on, and they'll be moved into the next room. And people behind them will come into that room and have the same experience they just had. And by going through these 4 rooms, which are narrated by video and fully interactive and totally fun, by the way, they're going to have a great time. It's going to take them about 25 minutes to go through. We've tested it on several groups of people who've been our beta testers, and people seem to like it. So I want to describe each of the rooms before I tell you about how they're built. So in this first room, there's a lot of projection mapping. You walk into this first room, and there are fish swimming around on the floor. And you have to stomp on all the fish. And there's connects in the ceiling and projection mapping on the floor. And your goal is to get those blue fish that are swimming around and not stomp on the red fish. And the narrator's telling you all this, so you don't have to take my word for it. In the next room is a party table. It's a 6-player video game table, which is top projected. There are 6 trackball controllers, and there are several games that you can play on this. You can roll the trackballs around and race acorns or try and catch acorns, a couple different games. The third room is a laser maze, real, genuine lasers. You can take your eye out with one of those. Actually, they're eye-safe lasers, so you can't. And your goal in this room is to jump and dive over the lasers and get from one end of the room to the other end of the room and back as quickly as possible whilst breaking as few laser beams as possible. And you have to do this in a team setting. And the last room is our button wall room. There are 3 panels, each with 24 buttons. And on these buttons, we play a variation of Twister, where you have to sort of hit lots of buttons at the same time, or Whack-A-Mole, where you basically have to hit these things as fast as possible. Whichever ones are lit up, you smash them. This one's my favorite, by the way. I just like hitting buttons. So the TLDR on this, I guess, is that at every scale, this thing is written in Node.js and CoffeeScript. And it uses WebSockets to communicate amongst all the different devices. So as you can see from this very simplified and woefully incomplete system diagram, there are a lot of different systems here. There are hardware devices that are talking GPIO that are actually responsible for recording when you've pushed a button and responsible for illuminating lights when it's appropriate to illuminate a light on a wall. There are laser relay boards that are designed to send power to lasers, so lasers go on. There are photoresistors that measure the amount of light hitting a particular spot on the wall, so we know if a beam has been broken. There's projection mapping code, which is a little bit written in Node. The party table, which is a top projected game, as I said, running full screen in a Chrome web browser. But let me start at the bottom level and tell you about this device. This is called a BeagleBone. BeagleBones are totally cool. They're like Arduinos in that they have lots of GPIO. You can turn on 3.3 volts on any of those pins, and you can read analog and digital values on those pins. But here's the cool thing. It's got Ethernet, and it runs embedded Linux, and it runs Node. And so with an Arduino, where I'd have to write this stuff in C, compile it, and upload it, I can SSH into this device. And once I've SSH'd into my hardware, I can run shell scripts. I can run Node.js applications written in CoffeeScript. And so I can read to these pins in Node. Node then functions as the bridge between my network, which is a WebSockets-based system based on the Bayou protocol. Anybody familiar with the Bayou protocol? Okay, so a Bayou is a channel-based publish and subscribe mechanism. Basically, you declare your intent to receive messages on a particular channel, and if anybody else on the network publishes on that channel, you'll get those messages. We're going to return to that in just a second. So with this beagle bone, I'm able to create, this is the back of the button wall. The back of the button wall, you can see wires for lights and wires for buttons, all converging on this little embedded Linux system, which is running Node and reporting back. So what does it report? How does it talk to the network? Well, so when a button is pushed, it's going to publish a network using Bayou protocol, which is readable by any other device on the network. The channel it's going to broadcast on from this button wall is device button wall 0. Button wall 0 has just had an event happen. The event was someone pushed a button. Which button was pushed? Button 4. Now it could be unpushed. When they let go, the corresponding event is emitted. Now, the other side of this is when the controller, whatever's controlling this game, wants to illuminate a light. It sends a message over that same network bus and says, hey, button wall 0, please light button ID 4. So this is just a dumb piece of hardware. All a button wall does is respond to network events telling it to illuminate a light and emit events when someone pushes a button. That's all it does. No game logic. Even though we're building games, we've intentionally kept all the logic as far from that hardware as possible, but we've still written it in Node. As a quick aside, you know what happens when you hit an electrical button? The electrical signal does not make a clean transition the way you might expect. In order to read the electrical signal appropriately, you have to what's called debounce that signal, right? Well, did you ever wonder where the underscore debounce method got its name? It comes from that electrical principle. And in this, I can actually debounce electrical switches using underscore methods. So this general pattern of having dumb hardware out at the edges, which is all controlled from a central server, is replicated throughout this entire network, right? So here you see laser sensors, right? A couple more beagle bones hooked up to photoresistors. As the resistance value changes, a message will be emitted on the network. Laser sense detected a beam break. Which laser? Laser ID 4. I can do all this from my beagle bone. These are relay boards. This is a completely different piece of hardware, yet still controlled using Node.js and CoffeeScript. When I want to illuminate a laser, I send out to my network, device, laser relay, method, light. Which laser? 4. And then this Node.js process communicates that intent via serial USB to the relay board, which sends power to the laser. The party table. Well, if you want to switch the current game, you emit your intent over that network. You tell it which web page you want it to load in the full screen Google Chrome window. And meanwhile, on that full screen browser, there's an iframe whose location can change. So I can basically control a web browser's location over the network. Now it's pulling from a local store of games to put them on the screen so the player can play them. I told you about video narration. So this entire experience is narrated by a character, this cute little wolf here. And the video players are all Raspberry Pis. Raspberry Pis are the tiniest little Linux computer you've ever seen. They cost $35. They're absolutely amazing. They also run Node, and I can run all the same stack on them. So they are listening to events over the network. If I want to play a particular video, I say, hey, Laser Maze video machine, play video of media ID Laser Maze room intro. And sure enough, that video will play on that device. I told you the doors open and close automatically. Well, I got relays hooked up to door openers. If I say, hey, device, door 0, open up, sure enough, the door swings open. I've got DMX controllers on this network. I've got a DMX controller to control all the lights and the fog machine. Lasers are only visible when there's fog in the room. If I want to turn the fog up, I say device DMX, cue the fogger. I can also cue any of the other lighting cues in my system. So you can see that throughout this system, there are many dumb devices that simply respond to a common language that, you know, some controller is orchestrating. So the question is, well, where's the game? There's no game yet. So the trick here is that all of these rooms, all of these devices need to work in perfect synchrony. Even though there's a group of people in each room, and these people are all doing different things, right? They all have to work together. Not only do the devices all have to synchronize, the video has to go on when the lights go down, and the button wall lights have to illuminate, and they have to wait for the pushes. And then at the end of the room, the door has to swing open, and the lights have to go down, and the people go into the next room as the other room is ending. There's a tremendous amount of software choreography that's required to make a system like this work reliably. And so there is the brain. This is the brain of our system. And it's basically a standard server. It is the loudest server you have ever heard. Unnecessarily so. For the amount of work that this device is doing, it makes an unconscionable amount of noise, which is why we locked it in a server closet. And so this system is running one very important process called Brain, which is written in CoffeeScript and Node.js. And it has 4 state machines running in it. One state machine for each of the rooms. And as time goes on, events will come in over the network and evolve this state machine. It will move from state to state to state. And when state transitions happen, it will send more events to the network. And so in this way, these 4 state machines are running each of the games: the button wall game, the party table game, the laser maze game, and the quicksand game. Because each of the devices on the network can be controlled so very simply, you wind up with game code that looks like this. When the room goes into the enter state, which is to say, people are walking into the room, what do? Well, we tell the door to open so people can walk in. What do we do then? We cue button wall cue number 16, which is button wall lights go off in a particular configuration. And then we extinguish all the lights on all the button walls. Publish device button wall, each wall ID, tell them all to turn off. And then we play the ambient music for the room. And that's it. That's how you start a room. And when you begin the room, when the game actually starts, you close the door, you mute the audio, and you go to another state in your state machine. When you end the room, you close the door, you cue a different lighting cue, and you play a video telling them how well they did. I'm going to move to the next slide, which is actual game code. So this is a little bit simplified for the presentation, but the button wall game, the hit the buttons as quickly as possible, oh my god, the number of buttons is increasing all the time, get them as quickly as you can. The code to do that, with the videos, with the lights, with the button pushes, with all that stuff, is right here. That's it. That's all there is. Because all I have to do now is use this Bayou client interface to tell my button wall to illuminate that particular light, or respond to a push event when a push event happens. And so by taking complicated hardware devices, written oddly in Node, and taking all their logic, making those devices as dumb as possible on the edges, putting all the smarts into that central brain, you wind up with games that can be tweaked so simply because all the logic lives in one place. So I mentioned that Brain is written in Node, and as such, it's also a web server. And there's a ton of data flowing across this network at all times. And all these rooms are in particular states, and they're constantly switching between states, blah, 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 blah. But I can monitor all that from an iPad. So I can walk around this place, and I can investigate in whatever depth I want the state of my game system. So on this particular slide, you can see there's basically a section for each of my rooms. I can see what state that room is in. I can tell it to restart the room, enter the room, end the room. I can see how many people are in the group that's currently playing that room. And then for each of my rooms, there's several other buttons I can use to trigger lights. I can trigger the games manually, things like that. Just a general debug console. And then there's a put it to sleep button, which basically tells the entire experience to go to sleep at the end of the day. And all of those messages that are flying across the network, well, I can see them. I can watch what my hardware is doing in real time from this iPad. And I can actually manually emit events over the network. So if I want to test something on the fly, I want to test my hardware device that I finished, well, I'll just type in something there, send it out over the network, and it is as though it came from the controller itself. So I was able to develop a whole bunch of game simulations entirely in the web browser before the hardware was even built. And, you know, it's written in JavaScript, it worked in the browser. Some of that same simulation code I was able to port right over to the hardware device itself. And it worked just like it did in the browser. All the devices on the network are reporting their uptime to the central server, so I can see, you know, the general state of things. So you can see all but two of my machines are online right now. But you can watch them in real time and see their status, and they're reporting their information over, reporting their status over statsd and graphing it on a graphite server. They're all set up with watchdog systems so that if a machine, for some reason, stops responding to that Bayou network protocol, the device will automatically reboot. So, some fun facts. Took us 30 days to build this entire thing from design to start of install. The total time it's taken us to install has been about 2 weeks, and I should mention that Wyatt Bushnell is still there, fingers frantically flying across the keys, finishing the installation. And there are cameras in each of the rooms, and we can actually monitor him from here. But I don't suggest that. It might not be pretty. And yeah, this afternoon, I teleoperated a smoke machine 1,000 miles away and watched the result on a security camera. It was totally cool. So that's Versix in a nutshell. And I'm Eric Gradman from 2-Bit Circus. If you have any questions, fire away.
Did you have to write non-blocking I/O drivers for the GPIO, or did that come with your hardware devices?
Well, turns out we don't use non-blocking at all. I mean, we're basically reading the entire state of the universe at a time because it all fits into about 6 bytes. So you can poll at that rate. Yeah.
Oh, and what was the graphing tool you said StatsD to what?
Oh, StatsD was something written by Etsy, which is a way of very quickly logging numbers of interest over UDP. They're sent to StatsD, aggregated there, and then sent off to a graphing framework called Graphite, which warehouses the data and makes it easy to graph. So every time a system reboots, I can see the frequency with which it does it. Every time a game starts, I can see that. I can see how many players are going through the rooms. Beautiful, completely incomprehensible at the moment graphs of all the data in the system. We're still working out how to use that best. Take your time.
Have you considered, I'm curious to know a little bit more about these boards, like if you, I can see why you might want to prototype, for instance, with all the logic running on a central server. But it's interesting to consider how much of that logic you could put on those boards. They could still emit events and still be coordinated from a central server, but like the light boards might be able to still play a game even if the central server were down by pushing the logic for that game onto there. But
Sure.
Are there limitations on those boards that make that, infeasible or?
No, there's no limitation. Certainly you could push all the logic to the edges. At that point, it becomes a systems administration task rather than a programming task. And I'm a much better programmer than I am a systems administrator. And so, as far as I'm concerned, I'd rather have one central point of failure than many central points of failure. There's always going to be a point of failure there. Like, if it stops communicating with the central system, you're pretty much screwed anyway. It doesn't need to continue playing. My sense for things is that if you're at the point where a button wall 1 room away has lost contact with the server, everything else is going to fail anyway. So I just didn't relish the idea of sort of Git pushing code all around the network. I need to test it. I'd rather have devices that were sort of plug and play. You plug a button wall in and it's done. You don't have to worry about it anymore. You don't have to touch that code, because when you find yourself touching that code over and over and over again because you want to change the game logic, you wind up in a place where you could potentially damage perfectly working hardware code. I want my hardware code and my game code to be completely separate. It's a good separation of concerns. And that worked out very well for us.
So you reboot the house
Hmm?
in that circumstance?
Do we reboot the house? Yeah. Yeah, the nice thing about the watchdog system that we have in place is that if that brain system goes down for any reason, if a heartbeat isn't received after for a particular interval, every single machine reboots. Hardware watchdog timers will overflow and the machines will reboot, and they will keep on rebooting until they come into contact with that central server. So a real quick way of getting everything to power cycles, just pull the plug on the brain, which is fun. It stops making the noise.